The topic of this video is going to be heating curves, which is basically a description of how the heat flows into a substance as you apply heat and how the temperature changes and how the phases change. Okay, so we're going to take the example of ice. So if you take ice out of your freezer, first of all, it's way colder than the freezing point, and so it might be at minus 20 degrees. Okay, so the first thing you can do is warm up your ice cube until it reaches the melting point. And then when it reaches the melting point, then it melts but stays at 0 Celsius. Okay? So when you have a phase change, there's heat going into the system if it's going from a solid to a liquid. And then once all the ice is melted, then the water starts to warm up from 0 degrees C up to, if we keep applying heat, 100 degrees C. Then once we reach 100 degrees C, the temperature doesn't change any for a while, but the water starts to boil. And so the temperature stays at 100 degrees C as long as there's some water there. Once all the water is boiled away, if we have kept the steam inside maybe a closed container like a pressure cooker, then the temperature can rise. Okay, so a lot of industries use steam boilers, which are closed containers, and so it's not just steam at 100 degrees C, it's very much heated up steam. So there's these different points on the curve, which we're going to label now. This is melting. Now the reverse process is called freezing. So when you freeze ice, you actually have to remove heat from the water to make ice. And the same goes with evaporation or vaporization. The reverse process is called condensation. So you have to apply heat to evaporate water, and that's how our bodies get cooled, is because our bodies provide the heat to evaporate water. The reverse process is called condensation. So when water goes from vapor to liquid, heat has to leave the water and it goes to wherever is colder than that steam is at that point. That's how steam cooking works. It transfers heat from this phase change. And so melting, freezing, vaporization, condensation. All right, and so on these points where the temperature changes, well, this is heating up liquid. So remember that this point where you're melting, you have both solid and liquid. When you're vaporizing, you have both liquid and gas. Here you just have gas, and here you just have solid. Okay, so we have the three phases of matter, and anytime we're changing the phase, we have a mixture of the two phases. We start with solid, we have some solid and liquid, and finally we reach all liquid, and so on. All right, so there are 5 separate calculations that you might need to do in order to calculate how much heat it takes to go from, say, very cold ice cube to very high temperature steam. And you calculate the temperature change, the amount of heat added based on whatever the appropriate phenomenon is. All right, so we're going to do an example, but this time we're going to do a different substance, and we're only going to do a couple of these. In principle, it's the same as doing them all. So we're going to do one where there's a phase change where the temperature does not change. Then we're going to do one where we heat up a liquid. All right, so the example we're going to do is ethanol, and we're going to start at room temperature. Okay, now ethanol at room temperature does not boil. It boils at 78 centigrade. All right, so the first thing we need to do is we need to calculate how much heat does it take to reach the boiling point. All right, and that's one of these little slopey things. And so in order to calculate this, we need C, the specific heat constant for ethanol. It's much smaller than it is for water, and that is, let's see, 2.46 joules per gram and degrees C of temperature change. All right, So we're going to calculate that in a bit, but the other thing we need to do is we need to calculate how much heat it takes to evaporate all of that ethanol. And so in order to do that, we need to know the heat of vaporization. Now the constant cannot have change in temperature because the temperature does not change. So a heat of vaporization is only going to have joules divided by grams. So that number is 841 joules per gram of ethanol. So really we have the change in temperature for this guy. We have the constants. So all we need is to know how much ethanol are we going to try to heat up and then evaporate. And so for this problem, we're going to do 15 grams. All right, so we're going to do 15.0 grams of ethanol. They're going to vaporize. So 15 times 841. I'll do explicit units analysis here. And that is 1956. We'll round off at the end. Joules, which is the correct unit. And up here I'm going to go ahead and calculate 15 grams of ethanol times the specific heat constant, 2.46 joule per gram degree C. The grams are going to cancel. And then the change in the temperature, which is 78 minus 25, and I believe that's 53 degrees C. And degree C units cancel. Okay, so that's how you know if you have a phase change or not. You're going to have degree C if you're not changing phase, but just warming it up in temperature. If you have a phase change, you won't have degree C in your constant or in your calculation anywhere. All right, and so that is going to require, when we multiply it out, 12,615 joules. And so the total amount of heat is going to be the sum of these two, and total heat. Now we're going to round off to three significant figures, because everything's in three significant figures, and that's going to be 14,600 joules. Okay, now so in principle, if the unit's calories, the constant will be a different number, but the result will be in calories instead of joules. And remember that the conversion between calorie and joules is that there's 4.184 joules equals 1 calorie. And the original definition of the calorie was that it was the amount of heat required to raise the temperature of 1 gram of water by 1 degree centigrade.